So the ratio test is yet another way that we can determine if an infinite series converges or diverges. So here's what we're going to do. Here's how the ratio test works. So we're going to let L, we just needed a constant or a variable, we're going to let L equal the limit as n gets big, and here's what the ratio is. So it's the absolute value, so we don't have to worry about signs. And we're going to take a sub n plus 1, so the limit of the n plus first term over the nth term. So we're going to do some funny algebra manipulations here, and we're going to look at what the limit of this ratio is. Okay, so if that limit, if L is less than 1, then we say that the series converges. If that ratio, if the limit of the ratio is greater than 1, then the series diverges. Now, if it equals 1, then our ratio test was inconclusive, and we have to go try something else, maybe an integral test or, I don't know, try something else. Okay, so let's do some examples. So we're going to determine, so I have 3 examples here. We're going to see if they converge or not. So what we want to do is we just want to find the n plus first term, so we need a sub n plus 1. So we're going to find a sub n plus 1 for all of these and a sub n, and we're going to make a fraction of them. And that's it. So n factorial, just in case, right? So this is our factorial. N factorial is what I'm saying there, right? And I'm not going to do it with n because that's too much, but if it was 5 factorial, right, that's 5 times 4 times 3 times 2 times 1. Okay? All right, and just in case you need to know, 0 factorial is defined to be the number 1. So if it comes up, that's what it is. Okay, so n plus first term. So a sub n plus 1. And I'm going to show you something kind of funky on that, right? So it would be n plus 1 factorial. Right? But that's the same thing as n plus 1 times n factorial. Right? If you think about that, think about it. So 5 factorial is the same thing as 5 times 4 factorial. So I kind of just did the same thing here. Okay? So here is my numerator, and now I have 6 to the n plus 1. But that's the same thing as 6 to the n times 6. Right? Multiply like bases, you'd add the exponents, that would get you back to the n plus 1. Okay, so here's my a sub n plus 1. I'm going to go ahead and write that up here. So I didn't leave myself enough space as per usual. So I'm going to have n plus 1, n factorial, 6 to the n times 6. Okay. Now we're dividing by a sub n, but right, that's going to be a flip and multiply at some point. So let's go ahead, right, this is my a sub n, so I can go ahead and flip and multiply that. So that'll be a 6 to the n over an n factorial. So here's the reciprocal of a sub n, and we're taking the limit as n gets big. Okay, but before we do that, right, we're going to go through and we're going to cancel all those common factors. So 6 to the n goes away. N factorial goes away. And I'll come on down here. So what I'm left with then is the limit as n gets big of the expression. I have n plus 1 that's left and over 6. Okay, so when I take this limit, I get infinity over 6. That is infinity. Okay, so now we're going to come up and look at our chart. So my limit, so this is my L. Right, my L is infinity, really big. That is definitely greater than 1, so we would say that our series diverges. Right? L is greater than 1. Okay, let's do the next one. 1 to infinity, n plus 1 over n squared plus 3, right? And the more you do these, the more you kind of get a feel for, I'm pretty sure this is going to, I think it's going to diverge again. We'll see. So a sub n plus 1. So that'll be n plus 1 over n plus 1 squared plus 3. Right? And then that here, I'll keep working down here, is going to be over, so then n plus or a sub n. So here's my a sub n plus 1, and here's my a sub n. Okay. So take the bottom, flip and multiply. So now we want to take the limit as n gets big of n plus 2 over n plus 1 squared plus 3 times n squared plus 3 over n plus 1. Okay, there's going to be some big hand waves here, just so you're ready. So if I look at the, just like my leading term for the numerator and the leading term for the denominator, right? Because when we do our limits as it gets big, that's what dictates, right, what the limit equals. I'm not going to actually multiply, but the top would be fine. The bottom, I'm not going to do it. That would just be ugly. But I could tell, right, the biggest term on the top is going to be an n cubed. So really what I'm looking at is the limit as n gets big of an n cubed on the top. And then on the denominator, I'm going to also have an n squared in my first bit, right? And then it'll multiply that in there. It'll also be an n cubed. So when I take this limit, that is actually equal to 1. So we would say that the ratio test here is inconclusive. We actually, inconclusive. So this one actually did, the ratio test was not a good test for this one because I got a 1 out. The ratio test doesn't really work for that one. So then I'd have to try something else. And I think what I would try, and I'm not going to do it for you guys, but you can go look at this video too. I think this would be a comparison test, or maybe even a limit comparison test. So something like that. I'm pretty sure it diverges, so you could check it against something that you know diverges, like the harmonic series, right? Okay. So last one. So hopefully we get one here that converges, right? I like to do a little of everything. So a sub n plus 1. So let's see if we can just write it all down this time. So n gets big. So a sub n plus 1 goes on the top. So that'll be n plus 1 squared over, right? So 3 to the n plus 1. That'll be 3 to the n times 3. Okay, a sub n, right, we're dividing by it, so that's a flip and multiply. So there's our 3 to the n over n squared. So let's see, 3 to the n's cancel. So I'm taking the limit as n gets big of, I have an n plus 1 squared over a 3 times n squared. So, right, the n plus 1 squared over the n squared, that all of that goes to 1 as n gets big. So my limit, my L value is 1 over 3, which is less than 1, so it converges.